Welcome to qnawire.
So for this problem, we are taking a little bit of some chemistry and balancing equations, stoichiometry, these concepts, and we're applying them to real-world concepts. So for this particular problem, we are looking and identifying air pollutants that are produced through combustion reactions. So air pollutants. And when we think about air pollutants, we can think about global warming, greenhouse gases, these sort of things, just so that we know our minds are in the right place. And this is a combustion reaction that takes place in an engine when gasoline is used for fuel. So when you're just running a car, it could be potentially a bus, even maybe a plane, although I'm sure that the fuels are different. This is the sort of chemistry that's taking place. So I'll just write out the reaction, which you can look up online if you would like to verify too. But we have octane. That's what we can use. Of course, sometimes we might have methane as a gas in other contexts, but here we're just looking at octane, which if we hear oc, that's the prefix means 8, and it's referring to carbon. So we have 2C8H18. And then we need oxygen, of course, for a combustion reaction. And the coefficient we have here is 25. 25 O2 for oxygen gas, of course, diatomic. And then through this reaction, we are forming water. And if we have the equation balanced, it's 18 water, CO2, which we would expect, right? Because we know that cars are bad for the environment because CO2 is released, which is makes the world hotter. It's greenhouse gas. And then we have energy, which of course is the whole purpose of this reaction. So we have energy in order to make a car move. So this is the reaction, and then we are just already discussed these different reactants and products, just familiarizing ourselves with each. So now we need to think, how would the production of the pollutants be reduced if more people used mass transit? So if we wanted these to be reduced, right? If we want the production of these to go down, that's what this little arrow is indicating here, that we're going to have less, then we need less reactants being shuttled in, right? So how can we have less reactants? Because if we were to increase the reactants, we would increase the products. This is how the chemistry works, right? If we have a process of making cookies and we keep on giving the people making cookies more flour and chocolate chips, then they'll be able to produce more cookies. If they have less chocolate chips and flour and milk and eggs, then they'll have to make less cookies because they have less to work with. So that's the same concept here. So in order for this to go down, we need to decrease the reactants. So we need to use less octane or less oxygen. So the key here is oxygen, we have not a finite amount. We have a certain amount in the atmosphere. And then octane is that's fuel, that's gasoline. So how can we use less gasoline? Well, this is where the mass transit thing comes into place. So if we use mass transit, then we're working through this chemical process a lot less times. Because let's say that of course, this isn't an actual accurate number, but let's say this happens 1,000 times per day, right? This reaction happens 1,000 times per day because 1,000 people are driving. Of course, it's way more than that. If we can decrease this to, let's say 500, or even let's say 50, if everyone took public transportation, then we're decreasing the amount of octane that needs to be used, right? This is going to be decreasing. So that means we're going to have less CO2 as an outcome. So that's how the stoichiometry works. If we're using less reactants because of mass transit, right? If we have more people on one bus, then we have more people per octane used, meaning we're going to have less CO2 being emitted. So that's the chemistry and stoichiometry behind this.